Hey guys, this is a quick review of what you missed in live session 5. I'm going to talk about the open topped box problem in this part. So if you watch your live session, you got to see us toggle around with this. However, I do want to go into some very basics. So when we're talking about this, we're obviously talking about volume. And volume we know is length times width times height. So when you look here, you can see in blue, we had this original length, which was 7. In red, we had this original width, which was 5. But we cut out these portions here. I'm going to move that. The portion that we cut out ended up being our height. So we have our new length, our new width, and our height. So in order to find these, we create this overall equation for the volume of a box, which is, or an open top box, which is x, your original length minus 2x, and your original width minus 2x. And that's because if we look here at the 7, we're cutting out x here and x here. So for this one, it would be 7 minus 2x, and it would be 5 minus 2x. And that's once again because we're cutting it off each time. So for this problem, we're going to say v of x equals x, 7 minus 2x, 5 minus 2x. And so this type of formula can always be used when we're talking about an open top box problem. So I wanted to show you how we did that. We also talked about making sure we understand our axes. So for this problem, notice here we even have x, and x, like I said, represented the side length we were cutting out. And so x axis would be side length of square cut out, which also ends up being your height of your box. And then our y-axis is actually the volume. And that's really important because that's what we're trying to find. So to put these things in clarity, we have this point here. And this point would tell me that the best x value would be 0.96 feet. And the max volume, so the biggest volume we can get here, would be 15.02 feet cubed. So that's just being able to completely understand everything that we're talking about. What we didn't get a chance to talk about in class was the domain and range of this problem. So I'm going to erase some of this stuff now that we've looked at it. We notice that what they gave us is only here. They only highlighted this red part. But we see that the function keeps going. That's because our equation, v of x equals x, 7 minus 2x, 5 minus 2x, is a full polynomial. It's infinite. It's going to keep going. However, this is the only part that's important to us. And it's because we have this down here. Now, we just said that the y-axis is equal to the volume. And so I think most people go, well, we can't have negative volume. And I say, okay to that, but why? And so if we look at this point here, and we look at our equation, that actual point, our 0 there, would be 5 minus 2x equals 0, because we know that's how we find them. So negative 2x equals negative 5, so x equals 5 over 2 feet. That's what this 0 here represents, is this here. Well, when we think about that in a little bit more detail, we got this from the 0 that was talking about our shortest side. We're cutting from both ends, and this is where I wish I could still toggle. We're cutting from both ends. Eventually, we're going to get to the very center. If we get to the very center and we're trying to cut out a square that big, we're going to cut out the entire side. If we cut off the entire side of the box, we don't have anything left to fold. So therefore, we physically can't create anything else. That's why this ends. So once again, that is the domain restriction. Because domain is your x values. And it ends here because physically we can't create a box if we cut the entire side off. So that was just a quick little review and some other information from the open top to box problem that we did today in class.